In this video, we're going to start talking about power factor correction, and we'll do an example of what power factor correction is. First of all, the reason why you would want to do this is that when you correct the power factor, you're taking an impedance whose power factor is something other than 1 and you make it equal to 1. And one of the reasons why this is desirable is when the power factor is equal to 1, the angle of the power triangle is 0, and that means your apparent power and your absorbed power, P average, are equal, which gives you a system efficiency. Nu here, symbol nu, is for system efficiency. And you know, if your angle is 0, P average and apparent power are just 1, the ratio is 1, so you'd have 100% system efficiency. The system being the circuit. And even though you know, you do achieve this 100% system efficiency when you correct the power factor, the main reason for correcting the power factor is to minimize what's called line loss, and we're going to get to, you know, what that means coming up. Probably not this video, but the next video. So underneath the dashed line here is a problem where we have a source, 117 RMS volts at 60 hertz, which means omega is 2 pi 60 rads per second. And this resistor and inductor, this non-ideal inductor, represents a motor. So as you can see here, the resistance of the motor is 50 ohms and the reactance of the motor, XM, is 86.7 ohms. So when you're doing a power factor correction problem, like all AC power problems, you need to come up with the power triangle first. So here we have our power triangle, remember, with P average, reactive power, and apparent power, and also this power triangle phase angle. And remember, as we've talked about many times, this angle is the same as theta z. So one way to do this problem is that since we were given the impedance of the motor, because we were given the real part and the imaginary part, right? The impedance is the resistance of 50 ohms plus J 86.7 ohms. Well, we can go ahead, put this into polar form, and if you do 50 squared plus 86.7 squared all square rooted, you'll get a magnitude of approximately 100. And then if you do inverse tan of 86.7 divided by 50, you'll see that the theta z is 60 degrees. So if we go back to the previous page, we now know that this angle, I'll write it down here, we know that the power triangle angle is 60 degrees. It's the same as theta z. So the next thing we can do is we can come up with the apparent power. Apparent power is just the voltage across the impedance divided by the current through the impedance. So we can get what this current is because we know the source voltage and we know the impedance. So the current that's flowing through our impedance, okay, I, well, that's just going to be the source voltage of 117 at 0 degrees divided by 100 at 60 degrees ohms. So that gives us a current of 1.17 amps at minus 60 degrees. Okay, that's the current flowing through our motor. Now, while I think of it, another thing we could calculate here real quickly is power factor. Okay, power factor is cosine theta. So cosine 60 degrees is 1/2. And it's lagging since it's a motor, right? Remember, lagging refers to a positive theta z, which is inductive. So you see this motor has this power factor before we correct it. So you'll see once we correct the power factor, we effectively make the power factor of the impedance equal to 1. Alright, so we got the current, and now apparent power is just the voltage across the impedance, which is the source voltage in this case, times the current for the impedance that we just calculated. So we're going to have 117, and since we want a magnitude, we don't have to worry about the angle. So it's 117 times 1.17, and that comes out to an apparent power of 136.9 VAs. Alright, so our hypotenuse of the power triangle right here is 136.9 VAs. So at this point, since we have this angle and we have one of the sides of the right triangle, now to solve for P average and QL, one way we can do it is just with basic trig, that we know the adjacent side is the hypotenuse times cosine the angle, and then the opposite side here is just apparent power times sine the angle. So let's go ahead and do that. That P average is just going to be apparent power times cosine theta, which is the same as the power factor. So you see P average is just half of our apparent power, which is 68.45. And that's watts. And then Q would just be the apparent power sine the angle. Okay, sine 60 degrees. Remember, this is 60 degrees that we got earlier. And that comes out to 118.6 VARs. Okay, now I just want to point out that you know, this isn't the only way to come up with the quantities P average and Q, the reactive power. We could have also found P average by I squared R. This current here flowing through the impedance is the same current through the resistance of the impedance and the reactance of the impedance. So if you take 1.17 squared times the resistance, 50 ohms, you'll get the same 68.45 watts. And then QL you could calculate by I squared X. So 1.17 squared times 86.7 will give you the same answer of 118.6 bars. So the key now, you see up to this point we haven't corrected the power factor. We just found the power triangle for the motor. So, you know, just real quickly again, here's our power triangle. Theta is 60 degrees. Here we have 68.45 watts. Here we have 118.6 bars. And then our apparent power is the 136.9 VAs. Well, the way that we correct the power factor is we make this angle 0. We're going to add a component to the circuit that will make this 60 degrees 0 degrees, and by making this angle 0 degrees, well, now your apparent power is going to equal your P average, that this 136.9 VAs is going to become 68.45. And the way we do this is by adding a capacitor. Okay, we're going to add a capacitor so that the QC of the capacitor is equal to QL. And just like in the impedance triangle where XC and XL counteract each other because they're 180 degrees apart, so if you have an equal amount of reactive capacitance and reactive inductance, the net result is 0 reactance. Well, it's the same thing here with reactive power, that if I have my if the reactive power of my capacitor in my circuit is equal to the reactive power of the inductor, well, I'm left with the net of no reactive power, which corresponds to an angle of 0 degrees. So in the next video, we'll start with how you calculate the capacitor value from setting QC equal to QL.